Okay, so good morning. Welcome to the first session of this last day of the conference. The title of the session is the ART and ARIMA of forecasting. So what is this session about? First, I introduced myself so many times during this conference, so I don't think we need to spend time here. So I will first introduce data mining in general, and then talk about specific forecasting problems, including, of course, specific data preparation for forecasting. Now, you see, when you start using these tools, everything looks very simple. So with a couple of clicks, with wizards and so on, you get your forecasts. However, in order to really use such a powerful tool, you need to understand how it works. So we'll talk about mathematics that is behind time series algorithm, starting with multiple linear regression, talking about moving averages, and then explain the time series algorithm, which is actually a mixture of two algorithms. ART, which means autoregressive trees, and ARIMA, which means autoregressive integrated moving average. So you see, with this preliminary mathematics, we will get understanding how these algorithms work, and also get understanding when it's better to use which algorithm. So at some point you want to use mixture, some point only ARIMA, maybe only ART-XP, and we'll see how we can influence on these forecasts with parameters of this time series algorithm. So what is data mining about? So data mining is data-driven analysis, which means you start with data. Don't suppose that there is some structure in advance, but you are searching for this structure. You are searching for patterns, and then you use these patterns for predictions. And you are doing this by using mathematics to examine data. And it's worth mentioning that, of course, like any area in IT business, data mining has its own terminology. So typically we analyze tables, right? And we will analyze a single table model. However, in data mining terminology, a row is called a case and a column is called a variable. So just naming convention. This naming convention comes basically from statistics. Now, data mining and statistics are not completely the same thing. Statistics is science, data mining is business. So what is the big difference? Well, the big difference is that with statistics, you evaluate some hypothesis, and no matter what the result is, you accept the result and say, okay, we accept it or rejected a hypothesis. In data mining, because it is business, rejection is not an option because you don't get paid. So you are just searching until you find patterns. But this is mostly because of, let's say, stupidity of the work. Even not finding a pattern is some information. This is very typically hard to say. Also, data mining is dealing, this is kind of general expression in data mining, with large data sets. Now you have to understand what does it mean, large data sets, from statistical point of view. Doesn't mean you are dealing with millions or even billions of rows. Now, with statistics, we have two general branches of statistics. Statistics for small data sets, which means typically 30 cases or less. And statistics for large data sets, which means 200 cases and more. Doesn't mean millions of cases. So with data mining, we are not dealing with that statistics. If you have, let's say, less than 200 cases, then typically it makes no sense to use data mining algorithms. However, you can still use some statistical algorithms. Also, not all data mining algorithms come from statistics. like neural net work come from. Networks come from artificial intelligence development. Even some things are from biology. Entropy is highly used from information theory. So we have a set of algorithms, and okay, most of them are based on statistics, and terminology is based on statistics. So one of the most important tasks of data mining is forecasting. Of course, every company would like to know how they will perform next year, helping doing better plans, better budgeting, and so on. Unfortunately, you have to understand that forecasting, like any other data mining method, is not used to give you, let's say, the final result. So you are not creating data mining applications. You are creating actually an infrastructure that helps you to learn. So with data mining, you learn how to perform better forecasts by yourself. And this is something that is many times hard to understand, especially for business people. I had many times these problems. For example, I had a fraud detection project for some bank. And they were immediately, asking me, so what kind of applications are we creating? We are not creating any application. We are just creating infrastructure so you will be able to learn. Why? Well, basically with fraud detection it is very simple to explain this. Because people who do frauds learn as well. So whatever you do will be obsolete in some time. So you are building infrastructure that helps you constantly upgrading your knowledge, finding new patterns, and so on. About forecasting, I will tell you another example of this kind of misunderstanding. Like 2 years ago, I had a request from an investment company. Of course, this investment company did a lot of wrong investments in last years, so they were close to bankruptcy. And they were asking me, can I create an application that would automatically forecast stock exchange shares levels and so on, and automatically buy them and so on. So I said, no, this doesn't work like this. I can build a system that will help you learning, so you will be able to do better decisions. I insisted, but this is not what we need. I mean, I explained it very simple. You see, if I was able to create such a system, why do you think I would sell it? Why wouldn't I just use it? It doesn't work like this. So this presentation is about this knowledge that can help you using time series in a better way, in a more informed way. So, data preparation for time series. These data mining algorithms are very intensive in mathematics, but they use very simple data structures. So time series is limited to a single table. Some algorithms like association rules can accept two tables, like one side, many side, orders, order details. This one is limited on a single table, and you need also to have some variable or some column that defines time. It can be integer, doesn't mean that it must be data type, but it has to denote time points. Okay? And the next question when you start preparing the data is, how much historical data do you want to use? And this could be very, very important question. And all these are decisions before you even start preparing the data and start implementing mining algorithms. Depends what you try to forecast. You see, if you forecast things that change frequently, then you don't want to include too much historical data, because then if you include too much historical data, you would actually forecast the past, not the future. For example, imagine that you want to forecast sales of mobile phones and you take last 10 years or more of data, you would probably get forecast that next year the best seller would be Nokia 6310 or something like this. And of course this makes not much sense. So in this case, you would either take a smaller data set, not going so back in the past, or you can also try to do forecasts on some higher level, not on specific product level. So maybe you can use some categorization, some taxonomy of products, and if you really want to use long-term data sets, so maybe you could use product categories like smartphone, not smartphone, touch screen, no touch screen, and so on, and try to these combinations. Also, if there is not taxonomy inside your data set, maybe you can create one by binning or grouping data. At least you can do this, for example, based on price, cheap or expensive. Also, time series data has classical decomposition, and depends on your task, you might want to get rid of some of these elements. So we decompose this time series data into trend data. Trend that actually shows me whether my sales is going up. Okay? And then we have seasonality. Of course, this is very typical for sales. For example, you have this seasonality before Christmas sales go up, then in January down. So this means like, let me try to draw it. With trend, you try to get this more or less linear function, or maybe even different function, but let's start with linear. So with seasonality, of course, you get this movement around this trend line. Cycles are the same thing as seasonality, just in longer intervals. So we have these economical cycles, like 7 years. And the problem with cycles is just one. You typically don't have enough data, or you can't use enough data because of other reasons to really get the cycles and extract them. So cycles mean like if economy is up, let me use different color, then this top will be higher and this will be lower, and then maybe economy goes slightly down. So this is what cycles give us. And then finally there is noise, or simply errors. It simply means that lines are not that smooth, so you have always some kind of additional hills and valleys around the line. Now depends what is your task. You might want to get rid of some of these elements. So for example, if you compare some amounts in some currencies, you maybe want to get rid of trend because of inflation to have a constant comparison. If you want to get the general picture how your trend is doing, you maybe want to get rid of influence of seasonality. See? So maybe you want to detrend or filter smooth data to remove seasonality. So for example, let's say that you want to remove this seasonality in sales. Maybe you can group data, the months in quarters. And then you can use smart grouping, not just January, February, March, but maybe better grouping would be December, January, February, and then March, April, May, and then June, July, and so on. This might be more interesting grouping. Also, another problem is standardization of time points. Let me show you this on the next slide. So this is another typical usage of forecasting is churn detection. So churn means that you want to, churn is subscribers that leave you, that don't use your service anymore. And this is becoming very important in many services. For example, like mobile phone providers, the market is basically saturated, so you cannot get new customers. You can only get existing customers from another provider. And of course, it would be nice if you would have this data from another provider, so you could forecast which are those who are about to leave. However, you don't have this data, but you have your data. You know who is leaving you, so you can use this data to learn what has the influence on these decisions on churn, and then try to prevent more customers to leave. So this is an example of data you got. We have this constant subscription, and then at some point, customer breaks the contract, doesn't want to use your service anymore. This is nearly impossible to analyze. You don't have standard time point. You don't have a point which you would predict. So typically you convert this in a table like this. So instead of having concrete months, you say these are months before churn. So this is the amount of churn, this is 0, and then we go 1 month before, 2 months. So now we have standardized time points, and we can do our forecasting. Next thing, okay, you can do mining on relational data, or you can also mine analysis services data directly. However, with time series we have a problem, because we need to get single table representation. And in analysis services we have this multi-dimensional cube representation, and we got many dimensions in the result of an NDX query. So this might need additional standardization into standard two-dimensional tables. So what you can do to use analysis services data? Let me show you examples, and we go here. So first, I will show you an example of very simple forecast in Excel, but I will not use Excel later anymore. So here I have an example to tease you, you see. So I have a history of sales for N200 bike model for this AdventureWorks DW demo database. And we have year month, which is actually an integer, but you see it denotes time points. And we have amount of sales in Europe, North America, and Pacific. And this is formatted as a table, so I can immediately analyze it using the forecast method. And you already know, I guess, that these data mining plugins are free for Excel, free download, but they don't make Excel a data mining engine. So I must have connection to my analysis services. Excel will simply send data to analysis services, create a temporary mining model, session mining model. Analysis services will train the data and find patterns, and Excel will then send DMX queries to find these forecasts. So my timestamp is year month, and I can also inform for better forecasts about periodicity. And I would say this is monthly because this is sales, so we have monthly. Maybe I could even say quarter because these are bikes. And that's it. You see, in this case, it's very simple to use. And I want to forecast 5 time units by default. So let me run this, and data set is very small, so this will be pretty quick. Okay, so this is basically a graph showing how my sales will perform in next 5 months. So in North America going up, and then pretty quickly down, and then straight up again. In Europe, slower up, but more up, and somehow staying pacifically up. If I go back to the source data, I can see this additional 5 forecasts added to the data. And you see, this is how simple it is to use forecasting with Excel data mining headings. And imagine now that you need to create a plan for next year or some bare budgeting, and many companies use Excel for this. Now this could be part of this planning procedure. Suddenly you get educated forecasts, not just, over the top, let's make 20% more next year. So this can help you do better planning. Now, let me create a new worksheet and show you the problem in analysis services. So I have the same data in an all-up cube, adventure works. Okay? I have the same data, and I will create a pivot table report. So basically, you see, I have this internet sales amount, and then I have multiple dimensions. So I get multi-dimensional analysis. So for example, I have, what did I have? I had customer geography, so I don't have region, so I will take country, two rows. And then I had products, right? And I had product categories. Like this. And then I can also add date. So calendar, this is delivery date, let me use this one. Also in rows and so on. And somehow I'm getting the data I'm needing. Now I should create some kind of latent report, and then I would be able to use it. But data mining works on SQL Server or analysis services data, so I would still need to export this to SQL Server. Well, let me show you how you can overcome this problem by not importing, but creating linked server in SQL Server. So this is MDX query based on this data. So I have country, product category, and I have order year only in this case, just to show you how you can get this in tabular way. This is MDX query, and I use only year 2007 and 2008. So MDX query, which basically can return up to 128 dimensions. So the important thing is to get tabular format, so you have to return only 2 dimensions, like I did in pivot table. And then go to SQL Server and set some properties. Allow using MS OLAP provider, OLADB provider in process in SQL Server. It means allowing that end users automatically use this linked server, and then create linked server to my analysis services. And this is actually, linked server is actually a stored connection string inside SQL Server. So this is connection string, use this provider, use this server, use this catalog. And then we have a couple of options which enable faster execution. So these are options that help query optimizer. So I say this analysis services is collation compatible. I have the same collation as SQL Server. This means, yes, I will access the data. So we need to optimize this if possible, and so on. So let's go execute these options, and finally you have to define how end users will connect from SQL Server to analysis services, whether will SQL Server impersonate them, whether you use any specific account. And in this case, I'm using option use self equals true, which means SQL Server will simply impersonate my account when I connect to analysis services from SQL Server. And that's it. Now, this is the query and the query result, and I'm using transact SQL open query function, which accepts two parameters. The linked server name, which is actually then transformed to connection string, and the second parameter is the query, which must be, of course, in the language that your source understands. And, of course, then we have a lot of casts. Why? Well, these are classical problems. Classical Microsoft problems are that teams are not working together. So data types of analysis services and SQL Server are mostly incompatible. Analysis services automatically cast the SQL Server data types, also integration services data types, but the opposite direction is nightmare. So also reading analysis services data with integration services is a nightmare. You only get strings, whatever it is, so then you have to cast it to appropriate data types. And now, of course, this is data prepared in a similar way like it was in Excel, so now I can use this view as a source of my time series algorithm. I will not even do this because I already have prepared view. So I already have similar view prepared, so this was just showing you how this could work in analysis services, but I got similar view where I have model and region together, time index, and then quantity and amount. These are just columns that were used to create time index and the auditing column. So I will use this view, but just to show you that even with time series, you can mine analysis services data just to have more problems. So now, time to go to mathematics that is behind. You saw it, especially within Excel, it was very nice. Couple of clicks, and I got forecasts. So what is going on behind? So let me start with linear regression. In a linear regression, we show one variable, like sales quantity, as a function of time. And this is simple linear regression. So this y is maybe sales, and this is time. Okay? Now, multiple regression means that the target variable is modeled as a linear function of multidimensional input vector of multiple input variables. So we have epsilon equals a constant plus slope multiplied by first variable plus slope multiplied by second input variable, and so on. So linear regression can be used actually to predict the mean value. These are continuous variables. So with linear regression, we are actually trying to predict the trend. We calculate the regression formula in such a way that we find this line in such a way that sum of all distances from the line is the smallest. Actually, sum of squares of all distances. Why? Well, because some distances are positive, some negative. So sum of distances by themselves would simply be zero. So this is what we try to get with linear regression. Now, the same way, like you can use it to forecast mean values, just I will not go into details, but a little bit more complex. Mathematics is you can also predict variation, variability. Instead of predicting just line, you can predict also the distances from the line. Okay? What about moving averages? A very underestimated technique should be used more frequently. I always remember on moving averages when I see that in modern cars you always get instant fuel consumption, which doesn't help you at all. It's simply too sensitive on whatever you do. You step just a bit on it and immediately goes to, I don't know, 30 liters per 100 kilometers. Step back and it goes to 0. So it doesn't really help you. You cannot learn how to drive better, how to consume less fuel. It would be much more useful if these peaks and valleys would be smoothed with moving averages. However, I don't know, maybe some car is doing this. I never draw a car that would use moving averages. So in any car I saw so far, this data is simply useless. This information is more or less useless, doesn't help you at all. So we have many different moving averages. First, we can define simple moving averages, like just define moving average as average arithmetical mean of plus 3 values, arithmetical 1. Then we have weighted moving averages. In this case, let's say we take plus 3 values, but we multiply each value by a weight. So we can put more stress, more importance on newer values and less on the past. And of course, sum of all weights must be 1. Okay. And then, very popular in economics are exponential moving averages. Exponential, where you see we have moving average, which is current value, multiplied by some weight, plus previous, not value, but previous moving average, multiplied by another weight, and again, sum of all weights equals 1. This is very useful, very many times used in economics in general, for forecasting already, but we'll see that we can do better than this. Also, I will show you later, remember that this is previous moving average, which then includes previous value and moving average from 2 pilot points in the past, which includes a value from 2 points in the past and moving average from 3 points in the past. So actually exponential moving average is including all of the history. Just the more you go to the history, the less importance on the value is you are using is added to the average. Now, based on this, let's define some useful operators. These are just, let's say, specific names. So we define lag operator as operator that operates on an element of a time series to produce the previous element. So we get the previous element. So with this lag, in this point, we get the previous element. Of course, we can express this also differently, that from previous we can get the current. And then we can use more than one previous element, so we can define lag polynomials. And in this case, it's not just a simple polynomial, so I can define point in time equals this, but then I also added error. So, of course, you can feel that this goes to the direction of this classical decomposition. So we can express that point in time equals some inverse lag operator multiplied by some points in some values in previous time points, and depends how many you want to use, you get the degree of the polynomial, okay? Plus error. I changed the order of this equation just because of one reason, because this is standard order in statistics. Start with error equals something. This is standard order. This was developed by two statisticians from UK, Box and Jenkins. So they used this kind of approach, which is now kind of standard, so I want to use it as well. And this is then just transformation, so we can even say include this last time point in my equation and express error as, or noise as function of previous time points using the lag operator. Now, difference operator is a very special case of very simple log polynomial. So we simply say difference between two time points is actually value in the current time point minus value in time point minus 1. And of course, we know that this value can be expressed with log operator. And then again, we can search for differences more in the past. Okay, so we can define also kind of difference polynomial. Now, what does it mean, difference, if I draw it? So with log polynomials, we could express noise. With difference, we can actually express trend. That means this is time point, and then it goes like this. This is the difference. You see? So we can express trend. We get linear line with difference. So now let's go back to multiple linear regression. So linear regression accepts as input, no matter if it's on single input variable or multiple linear regression, only continuous variables. Okay? So only continuous variables are used. The target variable, predictable one, must be continuous, and regressor is a variable used as an input and must also be continuous. Now, based on this multiple linear regression, this is still statistics. Now we are moving to data mining. The regression trees algorithm evolved. So what's the idea of regression trees? Why don't we use also some discrete variables in this analysis and use discrete variables to split population in classes. So for example, we have these predictions for sales amount and we use these previous values of sales amount. Why don't we simply do this based on region or country and include this splitting in our mining algorithm? So what we get is piecewise multiple linear regression formula. So if we don't use any split, then it's back simple multiple linear regression. And actually in Microsoft data mining, we have regression trees hidden in decision trees algorithm. Decision trees work on discrete variables only. As soon as you have predictable continuous variable and at least one regressor, it means at least one continuous input variable, decision trees are automatically converted to regression trees. Okay. And use these regressors, continuous input variables, to calculate multiple linear regression formula and use discrete variables to split the population and get piecewise linear regression. So in every subclass you get a function that fits better the actual movement of data. Okay. And I guess many of you have attended yesterday my Excel BI session. I actually used decision trees there, and I actually used two continuous input variables, age and yearly income. In Excel, this is simplified. In Excel, you cannot get regression trees from decision trees. Decision trees automatically actually bind my age and my yearly income, so no regression trees were used. You get regression trees only implicitly through time series algorithm like I did, but you cannot really create regular regression tree in Excel. This is limitation because it is simplified. Okay. Now, if in addition, you have also linear regression algorithm. You can also select, I will show you besides decision trees, you can also select linear regression algorithm. And this is just because of many people, many statisticians are used to use linear regression. This is multiple linear regression. So they wanted to have a shortcut. So linear regression is just, internally there is no difference. It's just regression trees with no splits. So if you use only continuous variables and have all of them as regressors, and you get no split in your regression tree, this is actually the linear regression. So this is just shortcut for setting algorithm parameters. Now, what is autoregression? We're coming there to ART. What is autoregression? Autoregression simply means instead of using different variables as regressor, use the same variable as regressor, just use the values in previous time points. That's it. So this is what is autoregression about. So we have one input variable, but in different time points. So if you prepare data correctly manually, you could even simulate or create ART algorithm with decision trees, actually regression trees. So this is an example. This transformation is done automatically. So this is my source data. I have month and sales of movies, drama, action, science fiction, and the quantity of sales. Okay? So first step that autoregression trees do is pivot this. So we define this is drama in current time point. These are action movies in current time point. This is science fiction movies in current time point. This is drama in time point -1. And this is first step. And next step, autoregression trees automatically define these movies in the current time point, or these categories in current time point as input, as predictable columns, and all others as input. So if you would create such a pivoted table manually and define this as predictable columns and this as others as regressors, you would actually get ART algorithm with decision trees. And again, remember we have this additional improvement that we can use also discrete variables, and discrete variables simply split this population, so we get this piecewise multiple linear regression formula for some variable, let's say here, greater than whatever it means and so on. Maybe this is age, so we get this piecewise multiple linear regression formula. Oh, and by the way, Microsoft calls this algorithm, there is slight enhancements, calls it ART-XP, autoregression trees with cross prediction. Why? Because you see, this drama is input for drama in the current data point, but also action movies can serve as input to drama in the current point. Because all of other columns that are not predictable are automatically used as input for any of the predictable. So for example, here you can see that in prediction for drama, we use drama movies in previous time point, then science fiction in 2 time points with like 2 and so on. Now I mentioned that exponential moving average is pretty popular in economics. So we declare also like next value is my exponential moving average. And then calculate it, right? And then just pretend that now I'm in next time point, okay? And that this value is then current value. By the way, what does it mean? So it means, let's say I have these time points, and now I want to predict time point 5, okay? So I'm using these 4 time points. Now for time point 6, I must have time point 5 calculated, and I'm using these time points. So it means I am calculating these forecasted values one by one in a sequence. And the more I go to the future, the more I use calculated, not the source values, which simply means that the more error I make. As I said, you can express exponential moving average only with values, say by simply exploding this as previous and then as 5, exploding and so on till you come to the first value. Now, in this way you can even calculate and reverse the formula to get the general number. Okay? Why I'm talking this? So, how would you calculate this kind of moving average with a efficient transact sequence? The problem is that you see, initially we are referring to previous moving average. So basic window functions don't help you, because you don't have access to this intermediate result. So in transact sequence, the simplest calculation is simply row by row using cursor, which is of course not very, let's say, not very good practice. You always hear do not use cursors. But in this case, this is the simplest calculation, and please note that when we do data mining, performance issues are completely different. We simply don't care about this regular SQL Server performance issues. You see, cursors are slow, but this is still linear algorithm. You are passing data only once. Okay? So who cares? You are limited to your sample 20, 30,000 rows, so who cares if it works 3 minutes instead of 30 seconds or whatever, who cares? And by the way, if this is not fast enough, then you should use something, some language that is row-oriented, not set-oriented. So simple. Use .NET, use C#, and you will get the performance. Data reader is .NET cursor, just 10 times faster than the SQL Server cursor. Okay. However, I realized lately that you can even do some additional mathematics and do set-based solution for calculating this exponential moving average. And I'm not having a solution yet, but I think it's doable. I think it's doable. This is more like training to get the idea, but also you can do this efficiently. Now we have all building blocks. We explained the ART XP algorithm. Now let's explain ARIMA algorithm. So we know we have this decomposition. We expressed error as function of lag and difference operators. And for lag and difference, we can define how much in the past we go. So we can define the degree of the polynomial. So P, we have 3 parameters. P is the number of autoregressive terms. So this means how many time points in past are we using for our forecasting with the lag operator. And D is the number of non-seasonal differences. So how many time points in the past are we using with difference operator. And also please note that we have also different errors. Every time point has different error. So we also can define that how many errors are we using in the past in the equation. So this is basically general ARIMA equation, exactly as Box and Jenkins wrote it. So we have this expression of errors, just that now error is on the right side, and it's not one error, but polynomial of errors, which is equal to polynomial of lag operator operating on previous values plus difference operator operating on previous values. Which simply means there is no one ARIMA equation. Based on these three parameters, we have different ARIMA equations. So we always write ARIMA like ARIMA and parentheses and three parameters. So what does it mean? We have ARIMA 0, 1, 0, which means we are using 0 autoregressive terms, 1 difference, and 0 errors. And I'm sorry, but I'm using expressions from Vox and Jenkins, and they made this great equation and everything, but then they made a simple error. This is not random walk. Random walk would be 0, 0, 1. This is linear function. And you know, this is interesting in a modern world, you know, when somebody makes an error and this somebody is an authority, then everybody repeats this error, so suddenly it becomes a rule. So we have one difference operator which actually gives me simple linear function, 0 errors. So 0, 0, 1 would be random walk. We just add error on every step. This is interesting, you know, these truths that are urban legends. Everybody knows them, but they are wrong. You know, for example, one of these very nice urban legends, you know, I guess everybody has heard this, that Goebbels said that if you repeat lie enough times, then it becomes the truth, right? So this explains this kind of behavior, yes? Unfortunately, this is an urban legend by itself. This was said by Lenin, not by Goebbels. You know, this is interesting, even this one is kind of urban legend. So, seems like, you know, in modern world, thinking and evaluating things over and over is not appreciated anymore. And this is what is my problem with current science. Like 10 years ago, even Pope admitted that Pope can be wrong. Apparently now, science is becoming like a religion, and scientists can't be wrong. So we have to, you know, retest everything. Anyway, this is not really important, but just the name is wrong. So I'm repeating it. This is not random walk, this is linear function. 0, 0, 1 would be random walk. And then the more we go higher with these parameters, the more complex names we got. Okay? So at some point we simply stop naming these equations and just say ARIMA 3, 1, 2, whatever. So ARIMA 0, 0, 0, 1, 1 is simple exponential smoothing with growth. 1, 1, 0 difference first order autoregressive model. But at some point then we just say, okay, this is the equation we are using. So, now we have all of the building points, so we can go and start using it. So this ART XP and ARIMA is built into time series. And actually time series is trying multiple ARIMA methods and multiple ART XP models. So multiple ART XP models means that it starts with different splitting of the data. If we have no discrete variables, then we get a single model. Okay? We have only regressor. And multiple ARIMA simply means try with multiple equations. So how do we know which one is the best? We try to remove as much noise as possible. So the idea is to minimize noise. So let me show you how it works. We know that I will use this V-time series view. And of course, I need my SQL Server data tools or Visual Studio. And I will create a new analysis services multidimensional and data mining project. Let's let's call it time series demo. Okay. So my data, yeah, I know. From yesterday we have the final version, I know, but I'm not updating until the end of the conference. I don't want to risk at the moment. So our data source is simply Adventure Rules W 2012 database, and I will just inherit, meaning I will just use service account for analysis services service account to connect to SQL Server for training, and impersonate me when I make forecasts. So my data source view, data source view is needed by analysis services to create source queries for training. By the way, has anybody tried to create data source view programmatically? No. Actually, data source view is ART.NET dataset. So when you create kind of analysis services database programmatically, you create ART.NET dataset, because this gives this metadata information to create transact sequence queries. So what I need is this v time series view. This is the only one I need. And I can start doing mining structure directly. So I will use existing relational database. You see, I cannot do time series directly from existing cube. Remember, that's why I have shown you the technique. So I will use time series algorithm, and this is my case table. And now let's see what I'm going to use as input and what is predictable. So first of all, I have model region, which is part of the key, and time index. Okay, and time index is also part of the key. And then I will use amount as input and predictable, so I will predict only amount. Or I could also predict quantity. Let's do it. We can always remove this on the viewer. And you see, these are the column types. I must have at least, minimally, I must have key time. Okay? And 2 continuous columns and 1 continuous column. This is minimum. So in Excel, we had only key time and 3 continuous columns. Here I have additional model region. In Excel, we have subset of data for a single model. Now I'll look forecasts for multiple models at the same time. So let's say time series, and let's say time series mixed. This is default. And here we are. This is mining structure. Mining structure defines general structure, so all models that share the same structure will have the same columns, use the same columns. Its mining structure is just a piece of metadata, like kind of namespace. It's not really important. So in an analysis services database, every model must have a unique name, for example. It doesn't go like mining structure.model. It must have a unique name. It's just for the tools. So if models share the same structure, it is easy to create a new model based on old one. So here I have my time series mixed. So I will just click on it and say new mining model, and use time series and say time series ART-XP, and then one more, and I will say time series ARIMA, time series. Okay. Now, let me check the parameters. So these are algorithm parameters that influence how your mining model operates. So let me enlarge this a bit so we can see all parameters, and let me explain what is this about. So remember, we have seasonality and cycles. So this is periodicity, okay? And we can leave the algorithm to try to find periodical patterns automatically, but typically it is better if we give a hint here. And this hint is actually a set of values. So I have one seasonality over months, and this would be my seasonality. So what if I know that I have also some larger cycles, like 7-year cycles? I will simply add here in this set the next value. You see, this is list of integers. My leaf level is month level. 7 years is 84 months. So this is how I get seasonality and cycle hint. I don't have this cycles here, so I will simply leave this as a single value. But it must be still in this parenthesis because it is a set of values that has only one value at the moment. Now what are others? So you see, forecast method by default is mixed, but you can also define which one. And there is prediction smoothing, which simply say how much ART XP and how much ARIMA is used. By default, half, and what does it mean, half? You will see this on the results. Now, complexity penalty. This prevents, you see, what could happen is for ART XP, I could have multiple discrete input variables. So I could split more and more and more and finally come to the point where I would make predictions based on a single case. So with complexity penalty, I'm preventing further splits. So this is one method. So if I raise complexity penalty, I will have shallower tree. If I lower it, I will have a deeper tree. Also, similar thing, additional parameter that can be used to prevent growth, at least to some parts, is minimum support. So I can even lower the complexity penalty and get a deeper tree, but then I raise the minimum support, so it means I will get deeper tree only there where I have enough cases, otherwise give me shallower tree in this branch. So this means only for ART XP. What else? The only thing I want to explain now is also missing value substitution parameter. So you see, remember ARIMA equation, we are using previous time points, simply means we must have them. No time point can miss. Okay? So what if I have missing data? If I didn't do something in ETL process, I can say, okay, just replace current value with previous or with a mean. Default is none, I don't have missing data. I will explain other parameters a little bit later. Let me just set periodicity hint and of course appropriate algorithm. So this one is called ART XP, so I will use ART XP algorithm only in this model. And here I will also add periodicity hint. However, I will use just ARIMA algorithm. Okay, I'm ready to go. Let me deploy this. And this is done, so let me see the results. And yes, this is CTP, okay? So what will happen now will be interesting. Yes. So, but I have other possibility because this is deployed. So these mining viewers, of course, work in Management Studio and also from Excel. So let me refresh this. So here are my mining models. Yeah, thank you. I know update is available. I will do it very soon. So let me show you, for example, this one. Let me browse the model. And let's try to get as good picture as possible. We will write the legend. And we have amount and quantity in the same graph, so let's try only with amount, for example. And you see by default I have 5 prediction steps. Okay? And these are some which were selected by default, and 200, Europe, North America and Pacific. But I have all other model region combinations, not just M200 in general like I had within Excel. Now let me also exclude this one because it's more or less constant, and let me raise number of prediction steps. And please try to remember the shape of these predictions, the shape of these lines. What you can see is the more you go to the future, the bigger differences are in prediction. This is ART XP. Okay? So let me show you what happens with ARIMA. And let's go to the future. What happens is, you see, ARIMA is using more and more linear approximation. Remember, ART XP was like this. ARIMA goes more and more smoothly. And what is the mixture? Of course, the mixture is the mixture. So we are using both ART XP and ARIMA. So we get differences bigger than with only ARIMA, but not so big as with ART XP. Okay. Okay, let me show you also the other viewer. In this case, I didn't have any. This is the regression tree, you see. So let me show the legend. So this is just for the ART part. This is viewer just for the ART part. And this is this linear regression equation used. So because I didn't have any discrete input variable, I didn't actually split this. I didn't create a full regression tree. Okay? So I have only one linear regression formula, but it also shows me the ARIMA equation. See, it's pretty complex. But this is actually, ARIMA is just constant equation would be for all nodes. Okay. So, the important is this one, right? And of course, I can also see this with DMX query, but this would be more complex. So it's here I see all of these equations, attributes, and so on. So I can get everything also with DMX queries, but I don't know, there might be quite complex to read this. But this would be how you would introduce this in your application. So if you would like to get forecast, okay, you don't just to read it. Just to for forecasting, you use DMX prediction query. You don't need to know anything about the content. Okay. So let's now move back to slide, and let's see why did we get those differences. Okay. Why did we get them, and which algorithm is better? Why would we use ART XP, why ARIMA, why mixture? Well, imagine that this is our actual set. So this would be very simple linear function. And this would be piecewise multiple linear regression. Okay? So what you can see that in this case, piecewise multiple linear regression, or ART XP, is actually fitting better the actual line. Right? Yes, but don't forget that we are using for forecasts more in the future, we are using more and more forecasted values. So, this good fit doesn't always mean it is the best possible. Imagine that we would stop here and this would be already forecasted. So ART-XP would go here. And suddenly it is much more far away from the actual line than ARIMA. And this is basic problem of ART-XP. The more you go to the future, yeah, the worse predictions are. And you can get even completely meaningless predictions. And all other parameters that I said I will explain later are just dealing with ART-XP. ARIMA, on the other hand, yes, it's great for long-term predictions, gives you less errors, but imagine that you have something like this. Let's say that these are mobile phones, so this was sales of one model, and then a new model was introduced, and goes like this. Now you calculate this over categories, so you group all of both models. So ARIMA gives you this. In this case, ARIMA gives you completely meaningless prediction. ART-XP would give you piecewise here, and then piecewise here, so you would actually get better predictions per model, right? If you would then use models for splitting the tree. So, what does it mean? We can get a general rule. General rule is that ART-XP is typically better on short-time predictions, ARIMA is better on long-term predictions. Okay? However, you should really know your data and what you are forecasting to select the correct mixture. Okay? To select, to prevent meaningless results. Okay, this is not completely meaningless. It's still average of the category. You can see slightly trend up. ART-XP can really give you, like here, completely meaningless predictions. Completely. So now you would use this. So next value is down. So next value would be even lower and lower. So definitely it can even could even happen that ART-XP would forecast sales below 0. You see. So in general, that's why we have additional parameters. And don't forget that you should also use data preparation part. So this can also influence on your selection of the algorithm. So if values are smoothed already in the data preparation stage, then usefulness of ART raises because you have less peaks and valleys. So you actually, let's say with moving averages, you actually moved ARIMA to data preparation. Simple ARIMA, you see. Seasonality. How does this time series use? So, time series uses 8 previous time slices plus 8 seasonal pieces of data, if you have it, to predict the current value. So, for example, we had monthly seasonality. So, for forecasting sales in December, it would use everything from April to December plus 8 last Decembers. So this way you get this seasonality included. Now, what next? Can you evaluate the quality of these forecasts? Well, there is only one serious way how to evaluate this quality is simply wait till the time comes and see how good forecasts were. So you should also always measure these forecasts. So the best thing you can do is simply include this forecast in some model cubes, and then you have actual values and forecasts so you can see the difference over time. And this is how you prepare your learning infrastructure. So you can improve your forecasts by learning where you made mistakes and get better and better plans and budgeting and so on. Okay. Now, of course, yes, you must have kind of smart, educated end users. Our government, for example, doesn't use any previous data for next year budgeting. No learning process at all. How could you evaluate or at least get idea how good a model is in advance? We have now 3 models. Which one should I use for actual planning? Well, there are some options. So first of all, remember that we can also forecast deviations. And actually this was already done by time series. So all I need is to show these deviations. And in addition, you can also just move in the past. So say, okay, now it's not April, let's pretend now it's January, and let's try to forecast April. And your hope is that if historical predictions were good, that also forecasts for May, June are good. So these are the methods to check the deviation and to check historical predictions. If you use these parameters to build these historical predictions, you will see in a viewer this like a single model, but of course internally time series created additional models for historical predictions. So also the training part is slightly different. So let's see these other parameters. Let me go back to my demo. Oh, let's see. Didn't reopen the project. Anyway, here we are. And let's change only this one. So let me explain these parameters. So what we have is, we already talked about how to detect periodicity, complexity, penalty, and forecast model. Historic model count, how many models do I want to build for the past? Okay? And what will be the gap? So I will say something like this. Let's go and build 2 additional models with gap 3. So I will build 2 models, one that goes 3 points back and one that goes 2 points back. So we start from there. Instability sensitivity, this is smart. This is very smart parameter, and which is unfortunately enterprise edition only. So this is smart stopping forecasting if you use ART experiment. So for example, in Enterprise Edition, if you use VMX queries, or if I would just select enough time points in the future, my line would break, would discontinue, because analysis services would stop making these forecasts. That makes no sense anymore. Additionally, you can simply define minimum and maximum series value. So please don't forecast anything below 0. Okay? And don't forecast, I don't know, if you are selling bikes and let's say something like there are 7 billion people in the world, so let's not sell more than 1 bike to everybody. Okay? And where is my periodicity hint? One. Okay. Okay, so let's deploy this. Probably I didn't say with this periodicity hint, so let's deploy. And then let's go to Management Studio, deploy process. Let's go to Management Studio and see the results. You can already notice that the processing was longer because I can build additional models, historical models. So let me go here and browse the mixed one. Hide the legend, go away, what I don't need. Also select only those who have comparable values. And then we come down. You see, show deviations. This gives you the information when you should stop using forecasts. And also let's have these prediction steps. And show historic predictions, just for one, for example. This one which was better. So you see, this is current time point and this is historic prediction. So, in this case, let's try some other one. In this case, this part is not very stable, while this looks much better. But it also means that you should be very careful how to use this forecast, even based on single group. Like here. Like forecasting Pacific quantity was much simpler than forecasting North America quantity. In this case. Okay. So, quick conclusion. Don't forget that you should always use common sense whenever you do data mining. You should have some idea what you are doing. Don't trust the tools blindly. However, if you implement everything properly, you can get a valuable tool that helps you learning and doing better and better, let's say planning, budgeting, better and better over time. And also, you can do it in, let's say, a little bit more advanced way with all of these parameters. Or you can even allow end users to do it directly from Excel in a very simplified way. Very simplified, but you don't have so much influence, but still it's valuable, still it's better than just creating plans over the time. So any questions? Yes?
In the beginning, you said don't forecast the past. I can understand the time shift. So if you say, oh, we'll take it back 6 months and see whether we got it right or not. But can you do it the opposite way? So you effectively reverse the data and analyze whether your prediction of going backwards.
Yeah, that's a nice idea. Yes, we could simply reverse the order of the key time, and then we could forecast any value in the past. Yeah, thank you. Good idea. Anything else? Yes, please.
Slightly related, but how do you get set up with the package that you got from Microsoft Time Series Analysis? Is that like an additional plugin or something that you need to purchase separately, or is that all built in?
Data mining, like for server side, you get it with analysis services multi-dimensional, and data mining add-ins for Excel are a free download. Just make sure that you select proper version, because there is version for SQL 2008 release 2, 2012, which works also on 2014. There was not separate release, but there is also a download for Excel 2007 and 2010 and 2013. Doesn't exist for Office 365, and also 32 and 64 bits. So the most important part is to select the correct version, and then it works. Otherwise, these settings are for free. And you see, data mining basic, enough for these add-ins, where you cannot influence parameters anyway. You get with standard edition, but for some advanced parameters, you need the enterprise. So I put something else on slide, because I have this. I had already pre-con seminar and 3 sessions, and I always forgot what I've got here for you. I got a free 1 month unlimited subscription for Pluralsight online courses, and I have these mini cards with discount code for 2 O'Reilly books books, Training Kit 7461, Creating Microsoft SQL Server 2012, and Training Kit 7463, Implementing a Data Warehouse. These are the last two books that I co-authored. So please take this. And of course, thank you for coming to this session and enjoy the rest of the day.